Welcome back to 3 Deviations and welcome to the last video in Unit 6. We are finishing off techniques of integration by talking about the second case of improper integrals, which is integrals over asymptotes. Also, fun fact, this is the 100th video for single variable calculus of 3 deviations. So if you've made it this far, give yourself a pat on the back. You are maybe halfway through, or maybe, yeah, about halfway through Calculus 2. So that's a pretty big accomplishment. So give yourself a pat on the back. So we're going to talk about integrals over asymptotes today, and we're going to go through a couple cases again. It's going to be pretty fun. Let's get started. So we've got similar definitions as we did from the last video, but these are a bit different. So instead of dealing with infinite regions, we are dealing with intervals where we have some continuity issues. So the first case, if there exists a discontinuity at b on the interval ab, then the integral between a and b of f of x dx is equal to the limit as t approaches b from the negative side. Remember the two-sided limits from the first or second video? Of f of x dx. So let's say for the first case, we have a graph here. We have A, we have B, we have something that looks like that. We want to integrate over that. Well, we are going to need to know what this evaluates to. It's usually going to be something infinite, so we need to be wary of what that is. Also, we have another case where if we have a discontinuity at A at the other side, then we do the same thing, but we take the limit from the other side. So we have the limit as t approaches A from the positive side of the integral from t to b of f of x dx. Furthermore, if we have a discontinuity at C between A and B, then we can split up the integral and then take the limits of both sides. Note that if one of these diverges, your whole integral is kaput. So you kind of need to throw the whole thing out. So if one of those, you can usually do one before the other, and then kind of see, and then that saves you some work. So it's kind of fast to do that way. Okay, let's get started with some examples. So the first example I want to do is the integral between 2 and 6 of 1 over the square root of x minus 2 dx. So as you can see, we're going to have a vertical asymptote at x equals 2. So we're going to need to make a limit there. As you can see, then we're going to have a square root of 0. That's no fun. Then we're dividing by 0. That's really no fun. Okay, so that's equal to the limit as t approaches 2 from the positive side of the integral from t to 6 of 1 over the square root of x minus 2 dx, which is equal to the limit after we anti-differentiate of t to the positive side of 2 times the square root of x minus 2, evaluated between t and 6. Okay, so now we can evaluate for 6, and then we need to look at this. So if we have t going to 2 from the positive side, so we have our square root function going to 2, then we're going to get to 0. So we're going to evaluate to 0, so we're just going to get 4. So when we evaluate to 0, then that really just is going to give us 4, because 4 minus 0 is 4. All right, so the integral, the integral does not diverge. The integral converges. The integral converges because it evaluates to 4. All right, let's try another example. Let's integrate between negative 1 and 4 of 1 over x minus 1 dx. So this is a case here where we're going to have a vertical asymptote at x equals 1 because we have x minus 1 in the denominator. So if we're integrating between negative 1 and 4, well, then we're going to have some discontinuity in between. So we're going to need to use that third case where we need to integrate both sides. But we're just going to integrate the first side. We're going to see what happens if we integrate between negative 1 and 1. So then we need to set the limit as t approaches 1 from the positive side of the integral between negative 1 and t, 1 over x minus 1 dx. That's a simple natural log integral, so we get limit as t approaches 1 from the negative side of the natural log of the absolute value of x minus 1, evaluated between negative 1 and t. Now we actually do need to use the absolute value because we have a negative being plugged in there, so we get the limit as t approaches 1 from the negative side of the natural log of 2 minus the natural log of t minus 1, the absolute value of t minus 1. And note, we get 2 here because we're taking the absolute value of negative 1 minus 1. Okay, so if we look at the natural log function, here are axes, the natural log function looks something like this. We come way out from negative infinity at 0, then we go up kind of like that. Now, as you can see, if I plug in 1 here, well, then we're really going to be in trouble because we're going in to a place where that's going to be 0. So 0, then that's blown way off to negative infinity. So this is going to diverge. So this integral diverges, thus the integral diverges. All right, we want to finish off by talking about some of the comparison tests. Now, this is something that is kind of helpful for this. I haven't used it a lot, but you're going to know a lot of comparison tests when you end Calculus 2, probably too many, more than you want. Let's get started with this one. So given that f and g are continuous such that f is less than or equal to g is greater or equal to g is greater or equal to 0 at x is greater or equal to a, then if the integral between a and infinity of f of x is convergent, then the integral between a and infinity of g of x dx is convergent. And likewise, we can say that if the integral between a and infinity of g of x dx is divergent, then the integral between a and infinity of f of x dx is divergent. So these are pretty helpful. These are pretty simple